Thanks, Lisa. Thanks, everyone. Welcome for joining today for the first core facility seminar of the spring 2020 semester. Hope everyone's doing well. Hopefully you just noticed we're recording. We're doing that so that we can have access to these recordings later on for folks who aren't able to join today. So please be mindful and mute your microphone or pause your camera if you're not actively engaging in the conversation. My name is Andrew Bernard. I'm the Director of Centralized Core Facilities here at UMass Amherst. We've been hosting these seminars for the last few semesters to provide awareness for the great work that's being done in our cores and to give you a chance to interact with both the core staff, learn about what they're doing, and engage with your peers to see how they're using our great facilities. Today, Dr. Weiguo Hu will be discussing some aspects of the NMR core related to the materials and chemistry capabilities. The facility also maintains resources and equipment geared towards biological researchers, which Dr. Yasna Fejo oversees, and we'll hear from her later this semester. Again, seminar is being recorded, so we'll be able to have access to it later on as we do all 3 semesters of core facility seminars, and you can get access to those. Lisa put the link in the chat to see some of the stuff we've talked about over the last couple of semesters. Encourage you to take a look and let us know if there's stuff you'd like to see in the future. Quick plug to say that our next seminar is going to be March 22nd from 2 to 3, and it's going to feature Jenny Beeman, the director of the Stonewall Center at UMass Amherst. It's a special seminar organized by the Center for Human Health and Performance on recognizing gender diversity in research. We're excited to have that up next. I'm going to be here monitoring the chat, so if you have questions you'd like to ask Weiguo once he gets going, please feel free to put them there. And once we get to a break point, we'll make sure we ask and get those answered. And you are welcome to unmute yourself in the Q&A section as well if you do have questions. So look forward to a lively chat. And with that, I'll turn it over to Weiguo.
Yeah, thank you, Andrew, for the introduction. Most of you know that NMR is a tool for structure elucidation, but NMR can also do some other things. So today I'll talk about one of the applications to study physical aspect for your molecule, and that is to study the polymer molecular weight determination by dosing NMR. I turn a page somehow. So let me new share. The standard way of studying like determining molecular weight for polymers is GPC. But the GPC method has a few challenges. For example, it's limited to like a few solvents. And so if your polymer can't dissolve in a particular solvent, you have a problem. Your polymer might interact with the column surface, then it might give you erroneous results, or it will not give you any results. Then sometimes your polymer have like a heterogeneous composition distribution, or like essentially you have a mixture of various stuff, then there's also a problem. And the like GPC column condition might change with usage. So you might need like constant calibration. Given all those challenges, NMR offers an alternative for this job. And the NMR technique that does this is called DOSI, which stands for diffusion ordered spectroscopy. So I'll talk about the principle of the DOSI NMR, and you might see like this method being referred to by some other name, like or DOSI diffusion NMR, PFG NMR, PGSE, and they essentially all mean the same thing. And I'll talk about some molecular weight prediction models and how to study like a molecular weight dispersity using the method, and like advantages and the limitation of the method. First, the foundation of the dosing method, which is gradient magnetic field. So let's see how it works. If you, like you have an NMR tube, let's say it's you lay it sideways and so that your Z direction is this way. So if you don't have any gradient or you have a homogeneous magnetic field, the field will be a constant as a function of the tube length. And the result of this is that you will have one single sharp peak on your spectrum. Then if you add a gradient? If you have gradient, which means the magnetic field strength will be dependent along the tube length direction. And because NMR signal frequency is proportional to the field strength, then instead of a sharp peak, you're going to get a rectangle on the NMR spectrum. And what's special about the rectangle? That the special thing is like a different part of the rectangle comes from a different part of the NMR tube. So for example, the bottom of the NMR tube experiences a smaller field, so it will appear at the left side of the rectangle, and then the top will appear at the right side. So this is essentially imaging. And so the entire MRI technology is based on this magnetic field gradient. And we can use this gradient to do our imaging of our molecules. The basic idea of a dosing NMR experiment is kind of like a spy movie. So in a spy movie, like you get a secret message from somebody of importance, and you encrypt your message into some secret code, and then you carry the code to a remote place, and then you give the message to another guy, and that guy will decrypt the secret message into a plain language, and you accomplish your job. And the dosing experiment is kind of like that. It has like 3 stages. So in the first stage, NMR signal will get encrypted into a special format called echo. And then your molecules will carry the echo and diffuse into a different place. And so usually you give it like somewhere like between 0.05 to half a second for the diffusion to happen. And over that time, usually your molecule might diffuse to a distance of maybe like a microns. And then you stop the diffusion, and then you will decrypt the echo into an observable NMR signal. So that's the dosing experiment. And then the encryption key is the location. So during the encryption, your molecules at its initial location, and that's its encryption key. And then in the third stage, in the final stage, the decryption key is the final location of your molecule. Yeah. So if your molecule is big and it hasn't diffused far away, your encryption key and the decryption key will be pretty much the same, and you will have your signal will not decay, so you have an original strength. Then if you have a small molecule and over that period of like half second, it has diffused to a pretty far place, that means your encryption key and the decryption key are different. And so you will get a attenuated signal, so that your signal will decay. And then since the definition of a location as I said in the previous page, is by gradients. If you apply a stronger gradient, you are going to get a stronger decay. Yeah, so this is the essence of a dosy experiment. And then you can do that systematically increment your gradient strength, and you will get a more and more attenuated signal. And so this is a plot for like 16 1D slices with the incremental gradient strength, and you see the signal decays at increasing gradient strength. And this sample here is a polystyrene with a molecular weight of 30K in a chloroform. And you can fit this decay with an equation. And this equation here, every parameter is known. The only unknown is the diffusion coefficient. So you do your curve fitting, and you can obtain the diffusion coefficient. Yeah. So just for every peak on your proton spectrum, you can do this. You can obtain a diffusion coefficient. So still the same example here, polystyrene with the molecular weight of 30K. So you can plot those diffusion coefficient on a 2D plot, and this is called a dosy plot. So in this plot here, the X coordinate is your chemical shift, and the Y coordinate is the diffusion coefficient. And as you know, like different signals belong to the same molecule diffuse at the same rate, right? Because they are all sitting on the same bus. So they all appear at the same row. So the signal here, this is the polystyrene, which has the slowest diffusion, and it will come on top. And then this signal here is some impurity, and then followed by some small molecule like solvent and TMS or tetramethylsilane. Yeah, so this is the dosy plot, and the orders by diffusion coefficient or size. And you can see this is almost like a GPC. The heaviest, the largest molecule comes on top, and followed by smaller and smaller molecules. And we can do this experiment for a series of standard samples with known molecular weight, and we can plot the molecular weight versus. Did I miss a page? Okay, here. And yeah, from the diffusion coefficient, you can use the Stokes-Einstein equation to calculate the hydrodynamic radius. And in the equation here, we know all these constants, and yeah, eta is the solvent viscosity, which you can easily find in any reference book. And here I have a table of some common solvents. And so you can calculate your radius, hydrodynamic radius this way. And so for this polymer here, polystyrene with 30K, we get a radius of the hydrodynamic radius of 3.93 nanometers. So this is truly a nanoparticle. And generally speaking, most polymers that we study have a hydrodynamic radius of like somewhere between 1 and like 15 nanometers. Yeah, then we can take a number of polymers with a known molecular weight, and we can measure their diffusion coefficients, and we can calculate the hydrodynamic radius, and we can make a plot. Yeah, so this is a log plot, and we can see all these data points fall on the same straight line. And this means that a straight line for a log-log plot means that they have a power relationship. And so this is probably a lot of you are familiar with this kind of a power law relationship. And in this case, the power here is the slope of this line, which is about 0.5. And as you might know, this is so-called the theta condition. And the molecular weight range for these samples is between 2K to 300K. Yeah, and out of this model, we can make our prediction model here. Yeah, so we have this equation in green, and then you can, it's ready for you to use. When you measure your, run your dosing and get your diffusion coefficient, and then you use your Einstein-Stokes equation to get your hydrodynamic radius, you can plug in this equation and calculate your molecular weight. And of course, this is assuming that you are using a polystyrene model. And we have also constructed models for polyethylene oxide and PMMA, and they all follow similar power law. Yeah, oftentimes, like the polymers that you guys make are not any of these polystyrene or PMMA, but some with some new structure. So which prediction model should I use? You could follow what most people do when they run GPC, go by the similarity of a chemical structure. Oftentimes you can, there are some alternative method that you could choose, like you could go by the similarity of backbone flexibility. One example here is that, like, suppose you have made this polymer here, which is like a polystyrene except a substitution on the aromatic ring. And so in this case, you can pretty safely assume that the backbone flexibility for polystyrene and your substituted polystyrene are the same. Yeah, so this means that if you have your polymer and a polystyrene have the same total backbone length, they would have the same hydrodynamic radius. And I think this would be really the safe assumption. So in that case, what you might want to do in terms of applying a model is to apply a degree of polymerization model, so which is directly related to the total backbone length. So you could convert this molecular weight distribution to a degree of polymerization distribution and apply this model here and predict the degree of polymerization for your polymer. Then you can multiply by weight per repeat unit to get the total molecular weight.
Does this degree of polymerization determine that your particle is not globular anymore, but elongated? Is that connected with it?
Yeah, so all of these polymers that I've talked about so far are random coils. Yeah, so the chains are basically doing kind of like a random walk in a solution. It's like a water snake in the water. It's not globular.
Can I ask a follow-up question?
Yeah.
Weiguo, so this Einstein-Stokes equation does assume that the molecule moves kind of as a spherical object, but I know you get a hydrodynamic radius and then you can compare that to similar polymers with varying molecular weight. So I guess that gets you past worrying about the overall shape. Is that right?
Yeah, so here you assume it has a spherical shape, and usually that's the case. Like I believe what happens is like if you have this random coil chain flopping in a solution, it diffuses as if it were a solid sphere, because it moves with the solvent that it carries around in the surrounding. Okay, so if like maybe sometimes you have made some polymer that is completely different from any of these like polystyrene or PMMA or PEO that our models were built upon. What do you do? Maybe like we could plot these three models on the same figure and see how different they are. And here, so we have a PS, PEO, and a PMA all plotted on the same figure. And you see that they actually are not that far apart. And like most prominently, PS and the PMA are like almost fall on the same line. And the PEO, despite its chemical structure being quite different from the other two, it's also not far away. Yeah, so you might just like apply any model and get a number, and which will probably, like, if you are only interested in the trend, it might be okay. So for example, if you get your RH of like a 5 nanometer, and if you apply all these three models, you find that the difference between the predictions is like a less than factor of 2. So if you are in the intermediate stage of research and you only need a trend, and it might already be good enough, any of the models. And many of you know that the same polymer dissolved in different solvents will have different dimension. And for example, like we know that a polymer in a theta solvent will have a smaller dimension than it's in a good solvent. So for example, polystyrene that has the chloroform is a theta solvent, and a benzene is a good solvent, and they have a different power law dependence, and the benzene will be slightly higher. So in that case, let's see. Let's see how different they are for our actual samples. So here I'm plotting the data for polystyrene chloroform as the black squares, compared to a model that was published by a Caltech group, the Grubbs group, as the red circles. And you notice that there's really pretty little difference. And I think the difference here, like according to the literature, the difference between a theta solvent and a good solvent is more pronounced at higher molecular weight, like when you get to like higher than 100K. And so at a smaller molecular weight, they are not that different. Not that different. Oftentimes, you've made a polymer that's of not a narrow molecular weight distribution. You might have a somewhat broader distribution of molecular weights. That means your polymers will have a variety of diffusion coefficients. And the result is, like, if you try to fit your dosage decay with a single component, it doesn't fit very well. So like if it's a monodispersed object, you wouldn't get a straight line on the semi-log plot. But if you have we have a distribution, you will see a kind of a little curvature toward the tail. So in that case, you could assume a certain distribution. For example, here I'm plotting a fit with a log normal distribution, and you can see the fitting in quality gets quite a bit better, and from the best fit, you could obtain the dispersity index. In this case, I got 1.5, which is not too different from the published 1.3. And you can also see the fitting quality toward the very end. There's a somewhat different, which I believe might be due to the actual molecular weight distribution. It's not really log normal, but slightly different from the log normal. All of you are working on polymers that are not linear. For example, some of you work on dendrimers. Some other of you work on like a bottle brush polymers. And how do you use those to look at the molecular weight of these polymers? And these are more challenging, and I don't think you can directly apply the models that I have just discussed. Those are ready for linear polymer in a random coil kind of a configuration in a solvent. So for example, for dendrimers, the power law dependence is usually between like 0.3 and 0.4 instead of a 0.5 to 0.6 for the random coils. In this case, you could still do something. For example, you could run those here at our NMR lab and obtain the hydrodynamic radius, and then you can go to literature to find a published molecular weight versus RH correlation model, and then make your prediction. I think that works. Should work pretty well, because these models, molecular weight versus hydrodynamic radius correlation, is universal, and it's not dependent on particular instruments or instrument condition as GPC. And like you could also add some other angles of investigation to like stitch together a more complete picture. For example, like if you work on a bottle brush polymer, these have you notice they have a lot of end groups, so they will have a relatively strong end group signal, and so you can integrate those signal and maybe calculate a number of the brush hair, and then you can combine that with your hydrodynamic radius, and those will together those will give you a more complete picture of the architecture of your polymer.
So Weiguo, may I ask you a question? So if the polymer is composed of the backbone of polymethacrylate, but with a different side chain, is it possible to use this use those NMR to measure the absolute molecular weight?
So strictly speaking, if your polymer is not exactly PMMA and you use PMMA model, there will be some potential error. So that will be up to your judgment. But as I have shown, the deviation might not be that big, and oftentimes might be sufficient to you. And yeah, if you have actually those polymers, and come to me, and we can discuss whether how safe you are.
Sure. I got it. Thank you.
Mm-hmm. the advantage of the dosing NMR method include like any solvent is okay. Any chemical structure is okay as long as they have proton NMR signal. Prediction models are independent in instruments and their conditions. Yeah, so then as a result, you could get a correlation model from literature and run the dosing here and make the prediction. And these models actually are quite available for a lot of polymers. And so from what I've seen, like these include like polyisoprene, polybutadiene, polyisobutadiene, like dendrimers. So a lot of those have been researched. And so it's, I think the tools are quite ready for you. And then convenience. So for example, you could take the same NMR tube to run proton carbon to get structure and then run the dosing to get molecular weight. Yeah, in the same time slot. And the total you might need less than 1 hour to get all the results. Often there's no need to purify your sample because dosing separates the signals for you. The different molecules will have different peaks, as you have seen on the dosing plot. There are also limitations of the method, which includes it's not an absolute method, and it depends on the choice of your particular calibration model, but so is GPC. It has limited ability to determine dispersity. So in this respect, it's slightly inferior to GPC. Higher molecular weight, for example, like greater than 300K, those result is less accurate. And you might not want to run your sample at a very high concentration because at high concentration, your little ball of polymers will bump into each other when they diffuse, and they will slow down diffusion, and you will get these erroneous molecular weight results. Usually, I would recommend something less than 1 milligram per milliliter. How to obtain a high quality dosing NMR results? There are 3 aspects that you will need to pay attention: sample preparation, conducting the experiments, and data processing. I will not go through the detail of these, but the main message I want to convey here is without very rigorous training, you can just simply follow my instruction and get a dosing NMR results of a preliminary quality. And then with some more practice and maybe with some conversation with me, you can get very high quality dosing NMR data. Other applications of dosing NMR includes, for example, you could easily separate impurities from target molecules because they belong to different molecules and they travel at different rates. You could study binding or complexation processes. For example, if your small molecules binding to a larger molecule, then your small molecule will assume the diffusion behavior of a larger molecule and it will diffuse slower. And you will notice that. You could study self-assemblies, and you could also study like dynamics of binding. So if your binding is not permanent, but it can come on and off, in that case, the diffusion coefficient that you determine by NMR is usually a weighted average between the bound state and the free states. So you can potentially vary your stoichiometry ratio or vary temperature and obtain a binding constant. To summarize, dosing NMR measures diffusion of molecules by applying a gradient magnetic field. So it's always it's a variation of MRI. It's a MRI of molecules. Molecular weight of polymers can be determined by running DOSI and applying a prediction model. And the model doesn't have to be the one that we created here at UMass. It can be anyone out in the literature. The dosing method overcomes a number of challenges. The GPC method, users can become competent with the model training and practice. And a report about the details of the prediction models will be uploaded to my blog soon. Finally, I'd like to thank the IOS core facilities seed project funding and Helen and Love for sample preparation, and professors Brian Coughlin and Todd Emmerich for discussion. And I'll be happy to take questions.
It looks like Lila has a question. Lila, do you want to unmute?
Yeah, I'm unmuted, I think, right now. Thank you very much, Weiguo. That was very, very clear, very nicely done. I have a question. I hope I didn't just miss it, but whether you talked about internal dynamics, degrees of motion within the molecule. So I know with a PFG experiment, you can have the spin diffusion take place because of rotations and internal motions, as well as the overall diffusion of the molecule. Did you say anything about that? I missed it if you did, but I would think it would enter in when you pick different peaks.
Okay, I didn't. Yeah, I think generally speaking, internal motions are not relevant. And yeah, because here the diffusion over a period of like half a second, the diffusion is like in the microns range, and the molecules are only in the nanometer range. So the internal motion is just too small length scale to affect the diffusion data.
So it's a combination of length scale and time scale, probably, right? Because the time scale for diffusion of the overall molecule is slow enough that they don't enter in.
Yes, over the time, I think that the length scale is just very big for the internal motion to show.
Thanks.
Yeah, on the other hand, like when you design your experiment, you still need to worry about like those T1 and those will certainly dependent on the internal motion.
Right. Thanks.
Stefano?
Yeah, thanks for the very nice presentation. I will have a practical question. You say the concentration less than 1 milliliter. Yeah. And what about the time? I mean, if the concentration is 0.5 milliliter, how could be a recommended time?
Okay. Yes, for simple molecules like a polystyrene, you can still get a very nice spectrum within half an hour. If you have a more complex molecules and you have low concentration, then you might need a somewhat longer experiment time. I would think like within 1 hour, maybe like 2 hours, you might have very good results. And I think the effect of concentration is actually not that big. So if you really care about like a very precise molecular weight, then you want low concentration. But if you just want a range, you can do well with like maybe 2.5 milligram per milliliter, and without introducing too much of error. Yasna? Yasna?
Weiguo, can you comment a little bit more on globular versus non-globular particles? Because what we are seeing in biological systems, often you have some kind of aggregation or polymerization in proteins, and you try dynamic light scattering and you get some numbers, but dynamic light scattering requires globular particles. So because it relies heavily on Stokes equation. So in order to apply DOSI in biological systems, in bio-NMR, we would need correction for non-globularity applied. And so can you comment a little bit more about that? Because for instance, if for any meaningful application to biosamples, we would need to solve that.
Yeah, so yeah, these, I wonder, like, you might want to like use like a modified form of the Einstein-Stokes equation. So that I think there are various form of those equations to account the non-globular shape. So in the case that I talked about, these are all random. These are all like a random coil configurations. So once they get to a long enough length, they are all spherical, and that assumption will fail at a very short molecular weight range. So that will no longer be spherical, and then there will be deviation. Yeah. So I think these are these are more details that we do want to think about.
Okay. Thanks.
Any other questions?
Yeah, I had just a real quick question, Andrew. Weiguo, it's Todd Emmerich. Very nice talk, very useful, I think, for everyone. And just one thing that occurs to me, because we agonize over solvent choice for GPC, and yet, water is water, and so, when you're in water, you're in water. So I just wonder about how much has been done in DOSI for synthetic polymers with salt effects, because it seems like you could just probe so much so simply, whereas with GPC, and aqueous systems with salt, you run into a myriad of difficulties. There might be a lot of literature that I haven't read, but I wonder just generally if that's something that there's room for probing.
Yeah, I think will probably be our next chapter in the report. Yeah, so like polymers with charged groups and solvents with salts. I think that general principle should apply. We just need a newer, a different model to make the prediction. I suppose.
Okay. Well, we can talk more about it, but it's definitely one area where I was thinking there could be a lot of fundamental things to uncover.
Yeah, sure. Yeah, we should do something along that line.
Whereas there's probably been a lot more probed with biomolecules, but synthetic polymers in water and combinations of them, et cetera, using some of these techniques. Anyway, seems like a nice area.
Yeah.
That might be a good opportunity to mention, Weiguo was kind to thank the IELTS group for seed funding that he received to do some experimentation here. For those of you who might be part of the Models to Medicine Center, there are funds available for trying some new techniques that might expand the course portfolio to new service lines or new offerings they haven't done in the past. So if you have some novel experimentation, but maybe not funding from an existing grant or one you're putting in for, feel free to reach out to Weiguo in the core facility and see if it's something that there's bandwidth where they might be able to try it. It's a way that we can return back to the core from some of the center's investments and make sure you get some good data for follow-on funding. So thanks for mentioning that, Weiguo. It's an important program.
Pleasure.
Any other questions? All right, well, I will start by saying thank you, Weiguo. That was excellent and good turnout. I'm glad to always hear good conversation. I thank you for being the first up this semester. I will remind folks again that our next seminar is scheduled for March 22nd, and that will feature Jenny Beeman, the director of the Stonewall Center here at UMass Amherst. And it's focused on recognizing gender diversity in research, a topic we're all learning a lot about. So it's a good opportunity to learn even more. So we look forward to seeing you there, and we look forward to staying in touch. Thank you all.
Thank you, Andrew.